Let's welcome Mr. Lin's report.
Good afternoon, everyone. Today, I'm going to present our research application of a novel deep learning convolutional neural network method to solve the.
turn on the user. Okay.
Good afternoon, everyone. Today, I'm going to present our
You
research
can touch this.
application of a novel deep learning convolutional neural network method to solve the unit commitment problem. This research focused on using AI technique to optimize power system scheduling under renewable energy environments. This is the outline of today's presentation. First, I will introduce the research background and the unit commitment problem. Then, I will explain the proposed NDQQ-CNN framework. Finally, I will present the experimental result and conclusion. Nowadays, renewable energy such as wind power and photovoltaic systems are rapidly increasing in modern power systems. However, renewable energy is unstable and difficult to predict. For example, wind power generation may suddenly decrease due to weather changes, while electricity demand can rapidly increase during peak hours. Therefore, power systems become more complicated and traditional optimization methods face significant challenges. The goal of this research is to reduce operating costs and carbon emissions while maintaining system stability. Unit commitment, also called UC, is one of the most important optimization problems in power systems. The objective is to determine which generator should be turned on or off, and how much power each generator should generate. For example, during daytime, renewable energy generation may be sufficient, so fewer thermal generators are required. However, at night, the system may need additional thermal generators to maintain power supply stability. At the same time, the system must satisfy electricity demand and minimize operating costs. However, the UC problem becomes highly complicated in modern power systems. Renewable energy such as wind and solar power are unstable and difficult to predict. In addition, the system must reduce carbon emissions and satisfy many generator operational constraints. For instance, generators cannot be turned on or off instantly, and their output power cannot change too rapidly. In addition, the system must maintain spanning reverse capacity to prevent unexpected power shortages. Therefore, traditional optimization methods become efficient for large-scale power systems. The evolution of UC optimization methods can be divided into 4 stages. Initially, classical optimization methods such as dynamic programming provide accurate solutions but suffer from high computational complexity. Then, meta-heuristic algorithms such as GA and PSO improve optimization speed, but they were prone to local optimal problems. These methods improve optimization flexibility, but their performance strongly depends on parameter settings, and they could still become trapped into local optimal solutions. Recently, AI-based methods improve adaptability under renewable energy environments. This is because reinforcement learning can continuously learn from dynamic renewable energy environments. Finally, the proposed NDQQ-CNN further improves scalability, convergence speed, and constraint handling capability. Therefore, the proposed framework is more suitable for modern renewable energy power systems, where both computational efficiency and system stability are important. This figure shows the proposed NDQQ-CNN framework. First, the system receives input data from the power systems, including generator status, load demand, fuel cost, and renewable energy forecast. This data represents the current operating condition of the power systems. Next, the QCN model extracts important features and reduces noise from complex renewable energy data, which help simplify system information before decision making. This is important because renewable energy generation often fluctuates significantly due to weather conditions. Then the DeepQ learning module learns the optimal scheduling strategy through policy learning. The agent continuously interacts with the environment and improves its scheduling decision during training. Finally, the system outputs a feasible local scheduling result while satisfying operational constraints. This means the proposed framework not only minimizes operating costs, but also maintains reliable power system operation. Overall, the proposed framework improves optimization efficiency under renewable energy environments. This objective function minimizes the total operating cost of the power systems. The optimization considers both economic and environmental factors simultaneously. This is important because modern power systems must not only reduce operating costs, but also satisfy environmental protection requirements. Economic factors include fuel cost and thermal generation cost, while environmental factors include carbon emissions cost and renewable energy curtailment penalties. Therefore, the proposed methods aim to achieve low cost and low carbon power system operation. This figure compares the CPU execution time of different optimization methods. Compared with traditional optimization methods, the proposed NDQQCN achieves the shortest runtime. This indicates that the proposed framework can solve large-scale optimization problems more efficiently. Therefore, the proposed method is most suitable for real-time renewable energy applications. The average execution time is approximately 81 seconds. Compared with conventional optimization methods, this significantly reduces computational burden for large-scale scheduling problems. This figure compares the total commitment cost of different optimization methods. As shown in the figure, the proposed NDQQCN achieves the lowest total operating cost among all compared methods. Compared with conventional approach, NDQQCN reduced the commitment cost by approximately 2.69% compared with DP, 2.17% compared with GA, 1.48% compared with PSO, 1.36% compared with ACO, and 1.11% compared with CGAN. This result demonstrates that the proposed framework can effectively improve both economic performance and optimization efficiency. This figure presents three optimization scenarios in the proposed framework. The first scenario focuses on minimizing operating costs. This scenario prioritizes economic performance and attempts to reduce fuel consumption. The second scenario focuses on minimizing carbon emissions. In this case, cleaner energy sources are prioritized to reduce environmental impact. Finally, the third scenario considers both economic cost and low carbon operations simultaneously. This combined optimization attempts to balance both economic and environmental objectives simultaneously. The result demonstrates that the proposed NDQQCN can effectively balance economic performance and carbon emissions reduction under renewable energy environments. In conclusion, this research proposed an NDQQCN-based framework for unit commitment optimization under renewable energy environments. Compared with conventional optimization methods, the proposed framework reduced operating costs by approximately 1.11% to 2.69%. In addition, the CPU runtime was reduced by approximately 41.8% to 59.5%. Overall, the proposed framework improved computational efficiency and achieved low carbon power system optimization. Therefore, NDQQCN provides a promising solution for future renewable energy power systems. Thank you for your attention.
Thank you. Thanks, Lin's report. Any discuss about this report?
What did you use deep Q-learning and QCNN for the UC program?
Traditional optimization methods usually suffer from high computational complexity when dealing with large-scale renewable energy systems. Deep Q-learning can continuously learn from dynamic environments, while QCNN helps extract important features and reduce noise from renewable energy uncertainty. Therefore, the proposed NT-QCNN framework can achieve better computational efficiency and adaptability compared with conventional methods.
Thank you. And any discussion more?
Okay. Could you move back to the conclusion? And the third reduced operation cost by just only the 2.7%. How to calculate the operating cost?
Because we consider about the low carbon emissions and also low operating cost. So it's the average cost.
Other operation cost is reduced just a little bit. And it's possible to reduce more.
If we want to reduce more, maybe we should generate more carbon emissions. But it's not very.
It's difficult to reduce more.
Because we want to maintain low carbon emissions, at the same time also maintain our operating cost.
Okay. Thank you.
Thank you. And any question more? Okay.
What is the main advantage of the proposed NT-QCNN framework?
The main advantage of the proposed framework is that it simultaneously improves computational efficiency, reduce operating costs, and support low carbon optimizations under renewable energy environments. In addition, the framework demonstrates better scalability for large-scale power systems compared with conventional optimization methods.
Okay, thank you. And any question more?
In your conclusion, you have several results. So my question is, which result is the most important in your research?
I think the most important result is the significantly reduction in CPU runtime. The proposed framework reduced runtime by approximately 41.8% to 59.5%, which demonstrates better scalability for large-scale renewable energy systems.
Thank you. And any question more?
Your student very excellent.
And that's Mr. Lin's report. Thank you. And finally, I declare that this meeting come to a successful conclusion. Thank you. Thank you. Thank you all.